Good morning. Um, we are getting really close to midterm 4, and so we want to do some review for midterm 4. Here is the review sheet that is in Canvas that you can take a look at. So let's go ahead and get started and take a look at some of these review problems. So in the first one, the first review problem we have here for midterm 4, it says that there is this background, or this low abundance, but steady abundance, of radioactive carbon-14 atoms, or nuclei, we should say. So there's 1.3 radioactive carbon-14 nuclei for every trillion carbon nuclei in living organisms. Now, why that's happening is, if an organism is living, and it's not maybe a bristlecone pine, this wouldn't necessarily be true for, but as long as I take that back, as long as the organism is metabolizing, it's going to be taking in new supplies of carbon dioxide. So, and that carbon dioxide is going to get cycled through the plant or the animal. And so what happens is, in the air, there is 1.3 of every trillion carbons in the air is the radioactive isotope carbon-14. And so as long as we're taking in samples of carbon-14, or if we're eating carbon products produced by plants, which we do, so the plants take the carbon dioxide in directly and incorporate it into, the carbon is incorporated into sugars, into proteins, well, the amino acids, into the lipids, all of the array of biomolecules that plants generate are going to have carbon in them, all the DNA and the RNA, and it's going to be with this abundance. Now, carbon-14 has a half-life that is 5,730 years. So again, it's not going anywhere really fast, and that means if something is biologically active, if it's metabolizing and taking in carbon sources, it's going to have this particular abundance. So it says, let's take a 50 kilogram person. Let's assume the person is 18% carbon by mass. I think I looked those numbers up. And so here is the decay. Did it say to show the reaction? It can't hurt, right? Maybe I'll get bonus points for this. So here is carbon-14 decaying into nitrogen-14, and well, it gave me the masses of both. So I wrote down the reaction, and there's the electron coming out. There's the anti-neutrino coming out. Here is my 50 kilogram person. 18% of that person is carbon, so that reduces it down to 9,000 grams of carbon. So I isolated all the carbon in that person, and it turned out to be, right? Yeah, 9 kilograms, of course. So I got like 9 kilograms of carbon in the person. Now I just want to count how many carbon-14s I have, because what they're asking me is what's the activity? Now, activity is the rate that decays are taking place. So in order to calculate the decay rate, or the activity of this sample, I need to take the number of carbon-14s and divide by the lifetime. So I can get the number by taking the 9,000 grams. Now remember, this is total carbon, so the molar mass for total carbon is going to be 12 grams per mole, and I should have written that in. Yeah. Okay. So I could have provided the molar mass for this. And then once I know that, I know that 1.3 out of 10 to the 12th is carbon-14. So we've seen that before in some other, when we did our other review of those later chapters. So it's an abundance ratio. It's a ratio of numbers for the different isotopes. Now, this is a little confusing. That's not carbon-12. That's 10 to the 12 carbons total. That is confusing. That's quite a coincidence it worked out that way. with a power of 12 here. Now here, that is carbon-14, but down here the 12 goes with the 10. Okay, interesting coincidence. So what it showed was that in my 50 kilogram person sample, that person has 587 trillion radioactive carbon-14s. Now that's not so many, because the person has an enormous number of carbon atoms in them. So having, 587 trillion carbon-14s, maybe it's not such a big deal. But we've got the number calculated. Let's calculate what the lifetime is. For that, I can take the half-life. Now, the half-life, it is there, 5,000, there, good. Half-life, 5,730 years divided by the ln of 2. That gives me 8,267. So I got it in years, and I'm kind of anticipating I may need this in seconds at some point also. So, in fact, I used that right away to get the decay rate per second. I took the number and divided through by the time in seconds. I got 2,250 decays per second. So what that number is telling me is seconds was the right unit to work in terms of. I would not want to leave that as years. That would give me a kind of a useless number. If I had a number that said, this decays at a rate of, 37 million per 10 years or something, then I have to stop and think, okay, what's 10 years? So putting this in decays per second and getting a number like 2,250, that works well. Now if it only decayed, 5 times per year, then 5 times per year would make sense. But it's many, many times per second. Second seems like the right unit to go with. So that's how many decays per second we're getting. In part B, they're asking for a Q value, and we've done a number of these beta minuses. And remember, I like beta decay a lot. So I do like beta plus, beta minus, beta neutral, alpha. I like alpha decays too. I like them all. But betas are my favorite. So anyway, doesn't mean an alpha decay isn't what's going to show up on the midterm, but be ready for any variety of beta decay also. Let's see, so I did the Q value, and we've done enough of these too. I can take the mass of the nitrogen-14 with the electron missing, add the electron mass on. It gave me a pretty low Q. So the carbon-14 and the nitrogen-14, their masses are actually really similar. They're, it's a really close tipping point kind of thing. Maybe it could have gone the other way, where nitrogen-14 decayed into carbon-14 and carbon-14 was stable. Anyway, that's what the numbers worked out to be for this. And then the dose. So the dose here, we are looking at what they're asking us to calculate a dose, right? What's the annual radiation dose? And the dose, this is annual, so that's energy per mass. Now the energy would be R, 2,250 decays per second, times the time. Now a year is 31.6 million seconds. Go ahead, try that, calculate it yourself. But 31.6 million seconds times the number of decays per second, and then times the energy. So 0.1565 MeV per decay. Put that all together, convert it into joules. So here is the MeV being converted into joules. Remember, it's 10 to the minus 13. Don't be off by a factor of a million. And that gives 0.001778 joules. And you're thinking, well, that's not so much energy. Even though they're decaying, 2,000 decays per second in this person, and that goes on all year long, it's still only a fraction of a joule, a couple thousandths of a joule of energy, ionization energy, inside this person, disrupting their chemical bonds. Okay, so there's going to be some damage due to this. The DNA could get injured, other biological molecules could be damaged. They all tend to get kind of recycled. And then for the DNA, there are enzymes gone back and forth along strands of DNA looking for simple fixes. If there's something that it's obvious what's wrong, that can be repaired too. So anyway, here is the total energy for the entire year. There's the year right there. And then the dose for the year would be taking all of this energy and dividing it by the mass of the sample that's absorbed this energy, or the mass of the sample in which ionization has taken place, the ionization energy. And that worked out to be 35.6 microgray. Now, to compare that with what you're supposed to take in during a year, I think you're supposed to keep everything, what is it, a millirad, something? You're supposed to keep everything within 1,000 or something micrograys for the year. So it's not nothing, but it's a pretty small portion of what the dose would typically be that you'd want to stay within for the year. And hey, this is something, all of evolution has taken place with carbon-14 decay going on the whole time. So organisms have learned to deal with this. I guess that's it for problem 1. Let's go ahead and take a look at problem number 2 here. So on problem number 2, this is kind of an interesting problem. It's talking about a different sort of fusion reaction that we might use in a power plant. So, a lot of people are familiar with like using deuterium as a fuel in fusion plants. This is a reaction that I just ran across many years ago, and it was kind of interesting, so I wrote it up as a problem. And so what's happening in this reaction is you have a target of boron 11, and then you generate a high energy proton beam, and you just keep shooting the proton beam at the boron 11. Now, if one of the protons hits and is absorbed by boron 11, it turns into boron 12. Boron 12 is not stable, and it breaks up into 3 helium-4s. So it's kind of an interesting reaction, and I thought it was interesting because boron's fairly plentiful. There's a town in Southern California called Boron, California, where they mine a lot of boron compounds. And then you really just have to get this proton beam set up. So anyway, looking at the numbers here, if you take a proton, now notice for the Q calculation, I've taken the proton and replaced it with hydrogen 1. So back to our standard of working in terms of the electrically neutral species. And so the hydrogen 1 plus the boron 11 in the reaction produces these 3 helium-4s, and I took the masses that I was given. Now remember, it's only the boron 11 that undergoes this reaction. On the other hand, of the boron that we find in nature, 80% of it is the isotope that undergoes this reaction. So it's not like uranium and fission, where a tiny portion is the isotope we want. In this case, the overwhelming bulk of the boron, or 80% of it, will react. This turns out to have a Q value of 8.683 MeV. That's not bad. That's a pretty good energy return on this. Now, I may have told this story already. Let me know. Tell me if I already told you guys this. But I had heard of this reaction, and I guess this was actually quite a while ago, because it was when my son was in, what was it, 3rd grade, and he came home one day, and he said, Dad, do you want to come on a field trip with my, I think it was 2nd or 3rd grade, my 2nd grade class? And I said, sure, where are you guys headed? And he said, he pulled out this paper from his little backpack and says, we are going to the nuclear engineering department at UC Berkeley. And I thought, really? You got a bunch of 2nd or 3rd graders taking a field trip to the nuclear engineering department at UC Berkeley? And I go, yeah, I want to come. I want to see that. And so when we got there, they gave us a nice tour, and the person actually presented a really nice description of what, they were doing fusion research. And so the person talking to us was talking about different fusion reactions, and so, you know, I had to push some third graders out of the way so I could get my question asked. And so I asked him about this. I said, so I've heard of this boron reaction, what do you think? And you know, he said, yeah, that is something that people have thought of as maybe promising, but that getting the proton beams up and getting the reaction to happen reliably enough has proven to be pretty difficult. But you know, at least at that time, and this has been some number of years ago, he said that you know, researchers were still looking into it as a possibility, but it just wasn't. You had to fire a lot of protons in to get the reactions to occur. Anyway, interesting problem. So there's the Q value, and then we kind of step aside and do a little bit of. This is almost chapter 41, maybe. We'll say it's part of chapter 42. What's the molar mass? And so we can take the abundances, multiply by the individual masses, and average that out to see what a molar mass is. Check that with a periodic table. So, you know, we've been saying that the periodic table is the average over the isotopes in a sample of whatever element we're talking about. And in this case, we're talking about boron. And when we average over the two prominent isotopes, we get 10.812, which is the number on the periodic table. Take a look. And then in part C, it says if we did build a power plant, let's build a power plant, how much boron would we need to get in order to operate the power plant for a year? So this is naturally occurring boron. So let's find out how much boron 11 we would need. And then we have to figure in, if we're going to get the boron 11, some of that is going to be boron 10 also. So we've got to adjust for that somewhere in our calculations. So let's try that. And so what we've got here is, I started with 1 year. It was an annual amount. This is the number of seconds in a year. We just had that discussion. And then this is the power rating of the, there we go, the 1,000 megawatt power plant. That is 1,000 megawatts. So 1,000 megawatts would be 1 billion joules per second. And then the conversion from joules into MeV, which I hope is becoming more and more familiar. And then each boron 11, assuming it reacts, will give us 8.683 MeV of energy release. And then for every 80.2 boron 11s, that's not a, these are not quotation marks, those are 11s. There's 100 borons, and a mole of boron has a molar mass of 10.8112 because we just calculated that. So putting all of that together, we ended up with, for the year, and that's a pretty good sized power plant, that's going to provide energy to a pretty good sized community. We need 508,000 grams and 509 kilograms. So, hey, that's only half a ton. You could haul that around in your truck, right? So you could bring in the boron. The boron's perfectly safe. The boron itself is not radioactive or anything. And so the boron could just be hauled into our power plant and put in, you know, wherever we're firing the protons in to generate the, to set off this fusion reaction. It's also kind of funny to call this a fusion reaction because in reality it's more like a break-apart reaction. But any of these reactions where we're working with isotopes of light elements near the early part of the periodic table kind of gets placed in the category of fusion, although it's kind of a break-apart problem. Nuclear fusion, that's what we're going to call it. Okay, for problem 3, here we go. So this is our problem from, we had a couple chapter 42 problems, Now we are looking at chapter 43, and it says in problem 3 that we have this particle. It's called a pion, and it's a bound state of a quark-antiquark. So immediately you're thinking, oh, that's a meson, right? There are things like protons and neutrons that are made up of 3 quarks, but this is a quark and an antiquark combination. Those are called mesons. So the pion actually is the lowest mass meson, but none of the mesons are stable, because if I have something made up of a quark and an antiquark, at some point the quark and antiquark can react with each other. And so it says here that the pion decays into a muon and a muon neutrino, an anti-muon neutrino. So it says for this reaction, now I always start with a Feynman diagram. Does it ask for that anywhere? It doesn't. But that's always useful to kind of organize the information. So here's the pion. There is the down and the anti-up quark. I got my arrows drawn so that the quark is in the direction of time, and the anti-quark line is in the reversal of time direction. I got some gluons in there holding them together. And then, since there was a flavor change taking place, you actually have to wait for the weak force to mediate this reaction. Even though you got a quark-anti-quark, they're not the same flavor. And so, since the flavors are different, we're going to have to be patient and wait for a weak reaction to occur. And that's why they call them weak. The weak force in nature just doesn't happen as readily as the strong force. And so there is that W. Now the W is going to be coupled to the formation of a lepton, anti-lepton. So let's run the numbers and see what we've got here. So if I look at the quarks going into the reaction, I have charges of -2/3 and -1/3, and that gives us the overall charge of -1. And then on the other side, we have the muon, which has a -1 charge, and the neutrino, which is neutral. And so that checks out. The electric charge matches on the two sides. We have -1 on the quark side, and we have -1 on the lepton side. Now, when we count numbers of quarks, because remember quarks are also conserved, the D is a quark, that's a +1, but the U is an anti-quark, and that gets a -1 in terms of quark counting. So we actually start with no net quarks. Mesons are no net quarks because it's a quark-anti-quark pair. And so we start with no net quarks, and that means in the products we should have no net quarks. And in fact, we don't have any quarks at all. That is not a quark, that is not a quark, so that's 0 and 0, and that works. So we had a quark-anti-quark that kind of canceled out the number of quarks present. And then kind of the reverse happened with leptons. We didn't start out with anything that was lepton, but we ended up with a lepton and an anti-lepton, so we've got to check the box on all 3 of those. All 3 of those we've been able to show are conserved. We have the same total number coming out of the reaction as what went in. Now I wrote down the masses up here, and they gave us those masses. So I've written them down, and they say the pion is at rest, and then it decays into these 2 particles. Since there's only 2 particles coming out, that's going to determine how the kinetic energy divides up exactly. There's going to be just one way that the kinetic energy can divide up. Now I kind of got ahead of things here. I didn't do part B. So let's take a look at part B. B said, show whether or not flavor is conserved. Quark flavor and lepton flavor. So we did show that electromagnetic charge is conserved, total number of quarks is conserved, total number of leptons is conserved, but flavors are not. And that's because if I follow this quark line right there, see how it starts out as a flavor of D, but it changes flavor into U along that path. So the solid lines are representing quarks or leptons, and the solid lines have to continue, they can't stop anywhere, and that guarantees that quark number will be conserved. But it doesn't guarantee flavor will. So flavor is not conserved if a weak reaction has occurred. So the D connecting to a U, and then on the other side, if we follow the arrows, we go from a neutrino flavor into a muon flavor. Those are two different flavors also. So not conserved, not conserved. Okay. Now the textbook, I feel like, in some ways kind of almost suggests that flavor will be conserved, but all of the reactions, all of the forces in nature do conserve flavors except the W, except the charged weak reaction, which does not. And it's a very common sort of reaction because if none of the other forces can apply, then you have to be a little more patient, but eventually the weak force can come in and change flavor and enable the decays to take place. All right, so for C, we are looking at calculate Q for the reaction, so we know how to do that. Mass of what we start with, subtract off mass of everything else. It says that 33.9 MeV of mass disappears and becomes kinetic energy. We're using in part D our kinetic energy formulas. We're being careful, making sure all the masses get put in the right formula. The formulas are written down correctly. And it says that in this decay, about 88% of the available energy that will be released goes with a neutrino. So that, a good check here is remember that the lighter particle, the particle with the lower mass in these two particle decays is going to get more of the kinetic energy than the heavier particle, and the neutrino is really, really low in mass, and the muon not so much. So the muon's getting 12%, and then those are the numbers it works out to. 29.78 MeV for the neutrino, and 4.12 MeV for the muon. Now, we're using the formulas from special relativity. We're bringing out the gamma factor. We put that in for the muon, and it says that the gamma factor for the muon, 1.0390, and that's going to enable us to calculate a speed. So that was the other item. Calculate the kinetic energies and speeds. So, and again, I feel like we've done a lot of review problems where we've used these formulas. And that's because this formula is really handy. And I feel like by, looking at using these formulas in different situations, you kind of get a feel for commonalities between the nuclear physics stuff and now the particle physics stuff that we're looking at. Now for the neutrino, since we've assumed it's massless, that's going to suggest that it's traveling right at C. So there's not much to be done with the neutrino calculation. And then finally that last part says, if, let's say in the reaction, instead of a muon and a neutrino, what if it was a muon and a photon coming out? Is there a way we could have a muon and a photon coming out? Or are there reasons to think that is not going to happen? And a photon coming out would mean that it's fine. The photon is electrically neutral, so no problems here. The photon is not a quark, but the photon is not a lepton. And that would mean that we're generating a lepton without generating an anti-lepton at the same time. And we currently have no evidence for that. So that would be big news. If there were evidence that we could generate leptons individually. Uh-oh, I think Laney fell off the table. Come on, Laney, hop back up here. You can do it. We just have a couple more problems. With the with a photon substituted into that, then it would say that lepton number is not a conserved number, and that would be enormous. That would be really, really, really big news. That would disrupt the standard model in a major way. All right. I I guess we're down to that last problem, so let's take a look. This is from chapter 44. Now, as I always tell, everybody, make sure you're looking at more problems than just the ones on this sheet. In fact, in this case, I've typically had more of these. And this time what I've got is I've got one set of problems for midterm 4. We'll take a break here in a bit, and then we'll come back. I have a set of practice problems for the final. And within that list of the final practice problems, there's some more problems relevant to midterm 4. But the final's not far off either. And so I'm going to go ahead and do that after the break. But let's wrap it up with this last problem, and then we'll take a break, and then we'll come back. So this is our diagram for expansion of space. And what they're telling us in the problem here is we're looking at light from distant galaxies, and looking at a particular galaxy, we find that the line in hydrogen, which typically is at 410 nanometers, has been redshifted to a wavelength of 550. Now, that's a more substantial shift. So I think back when we were looking at homework problems from chapter 44, the textbook had a problem where the galaxies were really not very far away, only several million light years, and the shifts were tiny. But here we're going to see a substantial shift. And so I'm pulling out all those formulas that we derived, make sure they're in your notes. And the redshift we're going to get is 550 over 410. And that ratio of the redshift, 1.3415. Now remember, the Hubble time, or the amount of time since the universe was in a hot, dense state everywhere, 13.8 billion years, or 13.7. We saw some examples using either of those numbers. And now the redshift that we've calculated based on our observations can be used to get ratios of xh over xo and also th over to. So those might come in handy. And also the other formulas that we've developed are rates of separation. So remember, this is not how fast a galaxy is moving through space. This is how fast two galaxies are separating as a result of expansion of space. So I put in the 1.3415, took a logarithm of that, multiplied by c. It turns out that with the redshift that we're showing here, 1.34, that is saying that where that galaxy is located and where we're located is currently expanding and carrying those galaxies away from each other at a rate of 0.294 times c. So that's pretty fast. And it can go beyond c. This does not have to be limited to c. You can actually have regions of space, if they're separated by enough distance, are separating at faster than c. Now, locally, nothing will be traveling faster than c in a local region. But if we look over at locations well separated by distance, they could be separating at speeds faster than c, much faster than c. If the universe is infinite, then if you look far enough out, and the galaxies just go on and on and on, then you're going to find galaxies that are, in the limit, they're going to be separating at infinite speeds. Okay. Let's see here. So using this redshift formula for time, we can work backwards and say that if currently it's 13.8 billion years, this light left galaxy A or B, whichever it is, at the 10.3 billion year mark into the universe. And again, 0 on our time scale is that hot, dense state, that high temperature, high density state of fundamental particles zipping around at really, really high kinetic energies. So to find x0 and xh, because they ask about distances here, let's see. How far away is the galaxy? Now, we talked about this. There's 3 different answers for this. So I think the safe approach is just answer them all. And so what you do is you go, okay, where was the galaxy? How far away were the two galaxies at the time the light left? For that, we can take v times t naught, because assuming a uniform expansion of space says that this is just going to be a straight linear function. So v times t naught gives us 0.294 times c, that's the v, times the 10.3 gigayears. Now, the factor of c slips inside, and the units become giga light years, which is kind of cool. The numbers here worked out to be 3.02. So when the light left, these galaxies were 3 billion light years from each other, and currently, now that the expansion has continued, and we continue to assume this is a linear expansion, then the current distance to that galaxy would be 4.06. So since the time the light left, the galaxies have now separated by an additional billion light years. Now, when we typically ask for distance, usually what we mean is something in between these two, and that is the time that the light actually traveled was th minus t naught. That's 3.5 billion years that the light was in transit, and locally, the light's always traveling at c. As light traveled through each region of space, it traveled at c. So the distance that the light actually traveled is 3.5. Is that 3.50? Not that we necessarily have 3 sig figs on these. Oh, I guess that is, that's kind of what we're left with. Okay. Sure, that's fine. We could have kept an extra sig fig, but we're down to 2. 3.5 is fine. Billion light years. So that's how far so, if you're the light, if you're the photons here, then when you started heading out to that galaxy, you go, oh, look, there's that galaxy. It's 3 billion light years away. I should be there in 3 billion years. But what happened in the meantime is that the space kept expanding. And so every region of space you go through was a little more distant than you had anticipated. And so instead of traveling 3 billion light years of distance and taking 3 billion years, instead you ended up traveling a total of 3.5 billion light years, and it took you 3.5 billion years to arrive. And when you did arrive, you looked back and you go, wow, it's a good thing I left when I did, because now it's 4 billion light years away. That would have taken me even longer. If I turned around and headed back to the other galaxy now, it's going to take at least 4 billion light years. And now I know it's going to take even longer, because space is going to just keep expanding. So the 3 distances, it's good to think in terms of all of those. Now, in part B, it says, let's imagine that there's a star in this distant galaxy, the one that we looked at with the 410 nanometers and the 550 nanometers. What's the surface temperature of the star? Oh, here we go. So the light from the star peaks at the intensity of the light peaks at a wavelength of 600 nanometers. So what we can do now is we can go back and we can use Wien's law. So the temperature then would be, the Stefan Boltzmann. Is that the Stefan Boltzmann constant? No, it's not. This is the Wien's constant. We'll call it that. The Wien's constant over lambda. And so I put those in, and the temperature, I guess I didn't calculate that temperature. Oh, I didn't do that first. Okay, so what I did first is I did the redshift, or I unshifted it. So if the light from that galaxy is reaching us, and it's at 600 nanometers, that's been redshifted. So I have to unredshift it. So I divided through by the redshift value that we calculated, the 1.34, and that left me with 447 nanometers. So that's the number I put in for the peak. The surface temperature of that star, if we went and visited that star and put a little thermometer in the surface to see what temperature it's at, would be at 6,484. So we're observing it as, what's 600 nanometers? So to us, the star looks kind of reddish, maybe a little orange. But if we actually went to that other galaxy and looked at that star, the star would be blue. Okay, so it's a blue star whose light shifted red. It literally shifted all the way into the red part of the spectrum during the travel. All right. Ooh, it seems like a good set of problems we went through, but it seems like not enough. As I was saying, I've got another set, so we'll take a break now, and we'll come back for the second part of today's class, the second lecture, and look at some more review problems. So let's take a break right now. If you guys have questions on anything, let me know.